Hello everyone, this video covers sections 2.8 to 2.10. Can I recall from last time what we did was mainly the conditional probability formula, which says the following. The probability that A is going to happen given that B already happened, okay, probability that A will happen given that B already happened is equal to the intersection of the probabilities divided by the probability of B. Alright, so in this section, when we talk about two laws of probability, we technically already talked about them before, so now we're just gonna be more official about it. Here, you just do a little algebra. You can see that the probability of A and B, it will be equals to the probability of A given B times the probability of B. And that's what we're gonna call the multiplicative law of probability, okay? So that will be the multiplicative law of probability, okay? Which you can actually also write this as the probability of B times the probability of A given B. Now, if A and B are independent, and again, this is not really new, we kind of knew this already. If A and B are independent, then that implies that the probability of A and B is just equals to the product of the two probabilities. Okay? Now this formula will work also if you have more than two events. So therefore, let's say you wanted to find the probability that A happen, and B happen, and C happen at the same time. So then this will be the probability that A and B happen and C. So you can break it down this way. So therefore, this will be equals to the probability that A and B happen times the probability that C happen given that A and B already happen. And then this part you can break it using the formula. So this will be the probability that A happen times the probability that B happens given that A already happened, and so forth. Okay. Now another way to look at this is, let's say that if they were not independent, if they're independent, this makes things a lot easier, you'll see right now. But let's say that this is the probability that the first person out of three that you ask that they like chocolate. So this would mean what's the probability that the first person likes chocolate and the second one and the third one. So that will be equal to the probability that the first one likes chocolate times the probability that the second one likes chocolate given that the first one likes chocolate times the probability that the third one likes chocolate given that the first and the second one likes chocolate. Now, if things were independent, then life is a lot easier, because if they are independent, then this is just equals to the probability of A, the probability of B, times the probability of C. So life is much easier when the events are independent. Okay. Now the second theorem is called the additive law of probability, or the addition rule of probability. And that says that the probability of it should be the union of two events, A and B, is equals to this. So we talked about this before. Remember, you have the sample space, and then you have the two events, and they intersect. The union will be whatever is in both circles. So notice how the interception, this one is technically added twice, so that's why I had to subtract it once. Now make a couple of notes here. So note one, if A and B are mutually exclusive, remember that implies that the probability of A and B is equal to 0. That means they have nothing in common. So therefore, the formula for the union is just equals to A plus B. And note 2, if A and B are independent, okay, so if A and B are independent, then the probability of the union would change to this. Okay, so you can change this to A times B. All right, let's look to the next example in which we're gonna use the two previous rules. So the question gives you this information. It says, suppose that A and B are two events such that the probability of A is 0.8 and the probability of B is 0.7. All right, so let's look to the first question. Is it possible for the probability of A and B to be 0.1? And the answer is no. Why? Well, remember that the probability of A or B is equal to the probability of A plus the probability of B plus the probability of A and B. And if we plug in the values, it is 0.8 plus 0.7 minus 0.1, which is equals to 1.4. This is more than 1, so a probability cannot be more than 1. So therefore, this is impossible. So you cannot have this if this is the case and this is the case. Okay, remember that any probability, doesn't matter what event it is, so the probability of anything always has to be less than or equals to 1, and actually greater or equals to 0. Okay. Okay, so using still the same information, what is the smallest possible value for the intersection? Well, given that the probability has to be less than or equals to 1, the sum of these two gives you 1.5. So that means that the smallest that A and B can be has to be 0.5. Okay, so using still the same information, so what is the largest possible value for the probability of A and B? Okay, so the value for A is 0.8, the area, and B is 0.7. Okay, obviously this is not to scale. So the biggest intersection you can have is when the smallest is inside of the biggest one, and the intersection still will just be the smallest one. So in this case, the biggest this could be is 0.7. So that implies that the biggest this could be is 7. So it has to be less than or equals to the probability of B, which is equals to 0.7. So therefore, clearly the biggest the intersection can be is 0.7. So if I ask you, is it possible for the intersection to be, let's say, 0.75, and the answer automatically should be no. All right, so let's ask one more at least. So what about this? Can A and B be independent? Okay, so can A and B be independent? Okay. Right, well, if they were independent, then the probability of A and B will be the probability of A times the probability of B, which in this case it will be 0.8 times 0.7, which is 0.56. Now, since 0.56 is in the acceptable range, and by that I mean the smallest this could be was 0.5, and the maximum it could be is 0.7, since this value is between the two, then the answer is yes, they can be independent. They can be independent. Okay. By the way, from now on, to say independent, I will write this symbol. I will mention this a couple times. So it's a perpendicular symbol. So this is going to mean A and B are independent, because we're going to use the word independent many times. So this is just to save some writing. So this will be the notation. I'm not sure if the book actually uses this one, but we will. Alright, so now let's go to section 2.9, which is called the event composition method to find probabilities. And the idea is pretty simple. And this is going to be the basis for the next section too. So you have the sample space, and let's say you have some event. Okay, let's just call the event D for lack of a better name. Okay. And then the event you want to figure out is D. But you can cut the sample space into two pieces. Let's say this is, I don't know, 1 and 2, where clearly you can tell that this is the opposite of this, or the complement. Okay, so these two are the complement, 1 and 2 are the complement of each other. So therefore this part right here, which I will highlight in green, that is technically D and I, or 1. And then this part highlighted now in yellow is technically D and I2. Okay. So therefore, if you want to figure out D, you find this probability and this, and they are mutually exclusive, so you just have to add the two. Now, it is very important to know that this part has to be mutually exclusive of this part. So if we look to the next problem, from this point of view, you will see that it will be pretty easy to solve. So therefore, in this problem, the question says, the items produced daily by a factory, 40% come from factory 1, which will be from here, and 60% will come from the other factory. And line 1 has a defect rate of 8%, whereas line 2 has a defect rate of 10%. If an item is chosen randomly from the day's production, find the probability, let's say the item is defective. Okay, so that's what we want to find. In this particular example, there is only two ways that the item can be defective. It either came from factory 1 and is defective, or it came from factory 2 and is defective, which is essentially this part and this part. Now, by the multiplicative rule of probability from the previous section, this is equals to the probability that came from the first factory times the probability that is that will be defective given that it came from the first factory. And we do the same thing with this one, so this will be the probability that it came from the second factory times the probability that is defective given that it came from the second factory. Now the probability that it came from factory 1 was 0.4, and if it came from factory 1, the defect rate was 0.08. Now if it came from factory 2, the probability they will be defective was 0.10, and 60% came from there. So all you have to do is multiply this, and the probability is 0.092. Now, part B, let's say, what's the probability that the item is non-defective? And essentially, you could do the same thing, because now this part means no defective. So this part is the intersection of not defective from factory 1, and this is not defective from factory 2. But the easiest way is to just use the complement. So the probability that will be non-defective, it will be 1 minus the probability that is defective, which you already found, and this is equals to 0.908. You should convince yourselves that you can do exactly this again, just changing d for the complement, multiplying, and you should get exactly this. So you should verify this by yourselves. Alright, so let's go to the next example. So suppose that the 2 defective refrigerators have been included in a sample of 6, in a shipment of 6. The buyer begins to test the 6 refrigerators one at a time. What is the probability that the last defective refrigerator is found on the 4th test? Alright, so let's define the following events. Let's say that G is going to mean that is a good refrigerator, and D that is a defective. Okay. Alright, so you have 4 refrigerators, and you wanna know what the probability that the second one will be found on the 4th test. So that means that the first defective one was found in one of the first 3 tests. So you have to look into all the possibilities. So it is possible, let's say that the first one was defective, and then it was good, then defective, so that's one way. Or it was good, defective, good, and defective. Or it was good, defective, and defective. Now let's look to the probability of the first one. So what's the probability that the first one will be defective, and the second one will be good, and the third one will be good, and the fourth one will be defective? Now using the formula from 2.8, so this will be the same thing as the probability that the first one is defective times the probability that the second one is defective, given that the first one was defective, and so forth. So then the probability that the first one is defective, it will be 2 out of 6, because at that point you have 6 refrigerators to choose from. Now you have 4 that are good, but you only have 5 to choose from. And now you have 4 to choose from, so it will be 3 over 4. And then finally it will be 1 over 3, because there's only one left that is defective. Right, also notice that the probability for this one and this one are identical to this. So technically you have this 3 times. So therefore the probability, the last defective is found on the 4 tests will be equals to 3 times 2 over 6 times 4 over 5 times 3 over 4 times 1 over 3. And here notice you can cancel this, and this is 3 times 2, so this will cancel that, this will cancel that, so this will be 1/5. Now it may be easier if you label this slightly different and say, okay, the 1 stands for the first test, D for the second test, 3 for the third test, and so forth. So this could make the notation a little easier, but it's not necessary. And this is what I mean. This will be the probability that the first test is defective, second one is good, third one is good, fourth is defective. Is the same thing as the probability that the first one was defective times the probability the second one is good, given that the first one was defective, and so forth. And the probability that the first one is defective is 2 out of 6, because you had 2 defective ones to choose from. You have 6 total. Once you choose one from here, you only have 5 left. So the probability that the second one is good one, given that the first one was defective, it will be 4 over 5. Okay? But again, it's not necessary to label in this way, but it may be easier. Okay, so now let's go to the last section, which is section 2.10, the law of total probability and Bayes rule. What we did at the beginning of section 2.1 was a special case of this, when instead of having k events, you only have 2. So this is the definition we have. For some integer k, b1 to bk, is said to be a partition if it should be intersection is empty, which means they are mutually exclusive. Okay, so what this means is the following: you have a sample space S, and you're gonna cut it in 3, 4, 5, 6, whatever the value for k is. So let's say k is 3. So this will be v1, this will be v2, and this will be v3. So notice that they are mutual or pairwise disjoint. So therefore, you wanted to find the probability of some event, let's say t, then you had to do what we did in the last section, but now you have to do it 3 times. The intersection with this one, the intersection with this one, and the intersection with that one. Okay, which is what the next following theorem says. Assuming that b1 through bk is a partition of S such that the probability for each partition is positive, then for any event A, the probability of A is going to be the sum of all the intersection with the partition. Now, the formula looks pretty weird because of the summation for some people. But this is essentially the formula we just did in the last section, but we did it only for 2 events. So for example, assuming let's say that k is 3, and if we look to the event t we have here, then the probability of t will be equal to the probability of v1 and t plus the probability of v2 and t plus the probability of v3 and t. And then using the multiplication formula, this will be the probability of b1 times the probability of t given b1, and so forth. The probability of b3 times the probability of t given b3. Okay? So this is not necessarily new. This is what we did in the last section. So this is now the general formula, and this is what is called the total law of probability. Okay. Now the last theorem we're going to look into is called Bayes rule, and notice that this relies or depends 100% on this right here, and actually on the total law of probability. So Bayes rule is just a special kind of conditional probability, which says the following: if you have a partition S such that the probability of each partition is positive, then for each I from 1 to k, the probability that the partition will happen, given that A already happened, it will be equal to this. Notice that this comes from the multiplication property, and the bottom is the total law of probability. Okay, so this is the total law of probability. Okay. So essentially, you cannot use Bayes theorem unless you have use the total probability also. So this is called base rule. Okay. Now you should think of base rule as a very special kind of conditional probability, which, like I just say, requires for you to compute the total probability first before you find the desired probability. So let's do an example of them. Okay, let's look to this example, which we did the first part already, which was the total probability, but let's do the whole thing again. But now it's asking you a conditional probability. It says, given that a randomly chosen item is defective, what's the probability that came from factory 1? So this is what we did before. The item came from factory 1 or factory 2. The probability that comes from factory 1 is 0.4, and therefore from factory 2 is 0.6. Now, if the item came from factory 1, it could be defective or it could be non-defective. Okay. The probability that is defective, it will be 0.08, which means the probability that is non-defective is 0.92. This was 0.10 and this was 0.90. Okay, so don't forget what this actually means. Remember, this means the probability that the item will be defective given that came from factory 1, while this means the probability that it will be defective given that it came from factory 2. And this is the probability that came from factory 2 and so forth. Okay, so it's a very good idea to label this. So this will be the probability that is not defective if it came from factory 2. So the question is asking the following: what's the probability that if the chosen item is defective, so now you know the item is defective, that it came from factory 1. So therefore this will be the probability that the item is defective and came from factory 1 divided by the probability that is defective. Now the top is going to be equals to the probability that it came from factory 1 times the probability that is defective given that it came from factory 1. And the bottom, we already did it in part in the previous section. But let me write the whole thing again. Remember, this was I times defective given I plus the probability that I came from factory 2 times defective if it came from factory 2. Remember, the bottom was 0.092, and on the top this will be 0.4 times 0.08, which this is equal to 0.3478. Right, let me add one more question to the question. If I ask you this means the following: given that you know that the item is not defective, what's the probability that it came from factory 2? So then this will be factory 2 and not defective divided by the probability that is not defective. Now we already calculated the non-defective last time, and it was 0.908. Then on the top, factory 2 and not defective is going to be 0.6 times 0.90, and the answer will be 0.5947. Now, one thing that is very important to notice here is the following. If I just ask you what's the probability that an item came from factory 1, where we know the answer is 40%, that's a very different question than asking if you know that the person is defective, what's the probability that it came from factory 1? And notice that the probability now is 34%, which is less than the 40%. Same thing here. This one is actually closer to the 0.6, but it's still not 0.6. But in this one, you can clearly see the this and this are very different. Okay. Right, so that's pretty much it. So you should give it a try to the following, which is the same idea. What's the probability that if it was not affected that it came from factory 1? And you should also try this yourself if it is affected that it came from factory 2. Okay? And that's it.